What if life is not a rare cosmic accident, but rather an inevitable outcome woven into the very fabric of the universe? Imagine for a moment that the emergence of life is not a fluke, a one-in-a-quintillion coincidence confined only to our little blue planet, but instead a universal destiny unfolding wherever the conditions allow. This question, seemingly simple on the surface, shakes the foundations of how we understand our place in the cosmos. It challenges us to rethink the uniqueness of Earth, the singularity of humanity, and even the nature of existence itself. Is life on Earth a remarkable anomaly, the result of a precise alignment of countless fortunate events? Or is it a natural consequence of cosmic laws bound to appear again and again, like patterns repeating in the vast tapestry of space and time? To grasp the depth of this question, consider the analogy of snow on a mountain peak. When snow blankets a summit in winter, is it just a random quirk of weather, a fluke caused by unpredictable atmospheric whims? Or is it the manifestation of underlying climatic rules? Temperature gradients, humidity and altitude interacting in a predictable dance that almost guarantees snow's presence in certain conditions. If life is like snow, then perhaps it too follows hidden rules. If the conditions are right, life must come to be no matter where in the universe those conditions arise. Throughout history, scientists have wrestled with this enigma. Early astronomers peered into the night sky and wondered whether Earth was a lonely oasis, or if other worlds might harbor life. For centuries, the prevailing belief leaned towards our uniqueness. The Earth, after all, seemed perfectly tailored to sustain life. But as our tools for observation advanced from powerful telescopes to space probes, evidence began to suggest that the ingredients and environments conducive to life might not be exclusive to our planet. Microbial life, hardy extremophiles, and complex organic molecules discovered in meteorites all hinted that life might not be confined to a single dot in the cosmic ocean. The possibility that life is inevitable carries profound implications. Imagine the universe as a vast, boundless garden, each star system a fertile patch where life sprouts in myriad forms. This vision transforms our understanding of the cosmos from a cold, empty void into a dynamic and living network. If life naturally arises wherever the right conditions exist, then the universe may teem with an unfathomable diversity of living beings evolving separately across space and time. It paints a picture of countless parallel histories of life, each shaped by its own unique environment, but all bound by the shared narrative of survival and adaptation. This shift from viewing life as rare to inevitable also challenges our philosophical and existential perspectives. What does it mean for humanity if life is everywhere? Are we simply one of many expressions of a cosmic principle, or does our consciousness hold a special place amid this abundance? The notion that life could be a universal constant forces us to rethink not only how we search for extraterrestrial life, but also how we define life itself and our own identity within the grand scheme. Yet despite all this tantalizing possibility, can we truly know if life is inevitable? The vastness of space, the limits of our technology, and the sheer complexity of life's origins all cloud the certainty. We are limited observers on a small planet trying to infer universal truths from a narrow vantage point. This uncertainty keeps the question alive, inviting deeper exploration and reflection. If life is indeed inevitable, the next puzzle lies in uncovering what conditions are essential for its emergence. What cosmic ingredients and environmental factors act as the catalysts for life to bloom? This inquiry naturally leads us to examine the basic building blocks and the cosmic settings necessary for life to take hold. An exploration that will take us deeper into the chemistry of life, the habitats beyond Earth, and the mysterious processes that transform simple molecules into living organisms. The quest to understand life's inevitability is not just a scientific journey, but a profound meditation on the nature of existence itself. We often take for granted the idea that life as we know it depends on a handful of key ingredients, water-carbon energy, and a suitable environment. But what if this familiar recipe for life is just one of many possible variations? What if our understanding of life's chemical and physical needs is limited by the narrow example of Earth, rather than reflecting a universal truth? The question of whether the ingredients of life are truly universal or unique to our planet cuts to the heart of astrobiology chemistry, and even philosophy, challenging us to reconsider what it means to be alive. The story starts with the elements we recognize as the foundation of life on Earth. Carbon, the versatile backbone of organic chemistry, forms complex molecules like proteins and DNA. Water, the solvent of life, facilitates chemical reactions and transports nutrients. Energy, whether from sunlight, chemical gradients, or heat, drives the processes that keep organisms alive and evolving. These essentials form a kind of cosmic grocery list for life, leading us to assume that if we find the same elements and energy sources elsewhere, life must follow. But is this assumption justified? Think of it like a recipe for a favorite dish. Imagine you're baking a cake. If you leave out the flour or sugar, you won't get the cake you expect. Maybe you get something edible, or maybe not. Likewise, life's chemistry might rely on a specific set of ingredients in precise proportions. Carbon's unique ability to bond in diverse ways is often seen as irreplaceable, but could other elements like silicon fill a similar role under different conditions? Water is prized as the universal solvent, but might other liquids, such as liquid methane or ammonia, serve as alternative life-supporting media in alien environments? And what about energy? Sunlight is abundant on Earth, yet some life forms thrive deep underground or near hydrothermal vents, drawing energy from chemical reactions rather than photons. Scientists have explored these questions through laboratory experiments, computer simulations, and the study of extreme environments on Earth. The discovery of extremophiles, organisms thriving in boiling hot springs, acidic lakes, or deep ocean trenches where sunlight never reaches, has expanded our understanding of life's resilience and adaptability. These creatures rewrite the rules of habitability and hint that life might spring up wherever energy and raw materials exist, regardless of conditions that once seemed too harsh. Yet the presence of these ingredients does not guarantee life, just as having flour and sugar doesn't always mean a cake will bake perfectly. The right chemical mix alone may not spontaneously give rise to living systems. The arrangement, the environment, and time are equally crucial. Life depends on delicate balances. Chemical reactions must proceed without being destroyed by radiation or toxic elements. Molecular complexity must increase to sustain metabolism and replication. And stable environments must persist long enough for evolution to take hold. If the recipe for life is common across the cosmos, then wherever we find these fundamental ingredients combined with suitable environments, life might be waiting. Planets and moons, with water ice, organic molecules and energy sources become prime candidates. Europa's icy shell concealing a liquid ocean, Titan's methane lakes, or even Mars' ancient riverbeds are not just geological curiosities, they are potential kitchens where life's recipe might be cooking. On the other hand, if life's chemistry is more flexible than we imagine, it might take forms utterly alien to us. Life might not require water or carbon at all, but instead rely on chemistry beyond our current understanding. Such possibilities force us to confront the limits of our own biology and imagination, reminding us that our Earth-centric view may blind us to other expressions of life that don't resemble anything we know. The implications of this inquiry ripple through science and philosophy. If life requires a narrow set of ingredients, it might be rare and precious, heightening our sense of responsibility to protect it. But if life is chemically versatile and inevitable, where conditions allow, then the universe could be alive in ways we have yet to comprehend, and our search for extraterrestrial life must be broadened beyond familiar markers. As we ponder these questions, it becomes clear that ingredients alone do not tell the full story. The stage upon which life unfolds, the environmental context, and the passage of time shape the destiny of life's emergence. What kind of environments foster life? How stable must they be? And for how long? This leads us to the next chapter in our cosmic investigation, exploring the habitats that might serve as cradles for life beyond Earth. Environments that provide the shelter, energy, and stability for life to take root and flourish. Imagine a world cloaked in ice, its surface shimmering like a frozen mirror, hiding beneath a thick crust, an ocean of liquid water warmed by tidal forces. Or envision a moon shrouded in a dense orange haze of organic compounds and methane lakes under a thick alien sky. These are not scenes from science fiction, but real places within our own solar system, distant and strange yet tantalizingly familiar in their promise to harbor life. What if these frozen or fiery worlds so unlike Earth are in fact cradles of life-alternative habitats, where life not only survives, but thrives in ways we are only beginning to imagine? When we think of life-supporting environments, our minds naturally leap to Earth-like conditions: liquid water, breathable air, temperate climate. Yet as our exploration of the solar system deepens, we discover that life might be less dependent on Earth's specifics and more adaptable to a variety of habitats. Take Europa Jupiter's icy moon, for instance. Beneath its frozen shell lies a vast ocean kept liquid by gravitational interactions with Jupiter, an internal heating system that defies the frigid temperatures on its surface. This ocean, hidden from harsh radiation by layers of ice, might hold the ingredients necessary for life-liquid water chemical nutrients and energy sources such as hydrothermal vents on its seafloor, similar in some respects to the deep ocean ecosystems on Earth. Farther out, Enceladus, a smaller moon of Saturn, surprises us with its spectacular geysers, shooting water vapor and ice particles from its south pole. These jets hint at a subsurface ocean, again warmed internally, capable of supporting chemical reactions that could fuel life. What is remarkable about Enceladus is that its plumes offer a direct way to sample this hidden ocean without needing to drill through thick ice, making it one of the most accessible targets in the search for extraterrestrial life. Then there is Titan, Saturn's largest moon, a world draped in a thick atmosphere rich in nitrogen and methane. Titan's surface is dotted with lakes and rivers, not of water, but of liquid methane and ethane, creating a radically different kind of environment. Could life exist here based on a chemistry utterly unlike our own, using liquid hydrocarbons as a solvent instead of water? This question challenges us to stretch the boundaries of what we define as habitable and alive, pushing us beyond our Earth-centric biases. These other homes in our cosmic neighborhood reveal the astonishing diversity of possible habitats. They are like different houses in the same cosmic neighborhood, each built with different materials designed under different rules, yet all potentially capable of sheltering life. This realization broadens our perspective dramatically. It forces us to ask, what does it mean for life to evolve in such alien environments? Would it follow the same evolutionary pathways as life on Earth, shaped by natural selection, mutation and adaptation? Or would it unfold along entirely new trajectories, driven by unfamiliar chemical processes and environmental pressures? If life does exist in these vastly different habitats, it may have developed forms and functions that are truly alien to us, organisms that survive in freezing oceans beneath kilometers of ice, or that metabolize methane instead of oxygen, or that communicate through chemical signals rather than sound or light. The implications are staggering. It suggests that life's diversity could be as vast as the cosmos itself, ranging from microbial ecosystems hidden beneath icy crusts to perhaps complex life forms adapted to environments that seem utterly hostile by Earth standards. This idea also reshapes our approach to searching for life beyond Earth. Rather than seeking carbon copies of Earth's biosphere, we are now looking for signs of life adapted to radically different conditions, for biosignatures that might be subtle or unfamiliar. It makes our task more challenging, but also more exciting, opening new frontiers in astrobiology and planetary science. Yet even as we explore these diverse habitats, the question remains, how does life emerge and organize itself in these environments? If the conditions for life's existence are so varied, what underlying principles guide the transition from simple molecules to complex, self-sustaining systems? This leads us to the next phase of our journey, where we explore the processes of evolution and self-organization, the mysterious forces that transform chemical chaos into the ordered complexity of living systems. Understanding these processes may hold the key to grasping not only how life begins, but how it adapts and thrives across the universe's myriad landscapes. How does the universe take a handful of lifeless molecules and transform them into something as astonishingly complex and vibrant as a living organism? This profound leap from chemistry to biology, from inert matter to self-sustaining life, is one of the deepest mysteries in science and philosophy alike. At first glance, it may seem like a magical transformation, but beneath the surface lies a fascinating story of gradual emergence, a symphony of chemical interactions that crescendo into the first whispers of life. Imagine the beginnings of life as a musical composition. At first, there are only simple isolated notes, individual chemical reactions happening spontaneously, unconnected and random. These reactions are like the fundamental tones, the building blocks of a melody. But as time passes, some reactions begin to interact, forming chains and networks, much like notes combining into chords and harmonies. Slowly, a pattern emerges, an increasing complexity, where molecules start to cooperate, catalyze each other's formation, and create feedback loops. This orchestration of chemistry gives rise to increasingly sophisticated structures, eventually culminating in something remarkable: the first protocell, a simple membrane-bound unit capable of metabolism and replication. In essence, life is a grand symphony composed over eons, evolving from humble beginnings to the intricate biological systems we see today. At the core of this transformation is the concept of self-organization. Rather than a single moment of sudden change, life likely arose through a series of incremental steps, where chemical systems spontaneously formed ordered functional arrangements. These arrangements were stable enough to persist and grow, harnessing energy from their surroundings to maintain themselves and replicate. Consider how crystals form molecules, arrange themselves into ordered patterns without any guiding hand, simply following the laws of physics and chemistry. Similarly, the early chemical networks that led to life may have self-assembled, driven by the environment's energy and the inherent properties of molecules. This process raises profound questions about the nature of life itself. Is the emergence of life a rare accident, a statistical fluke requiring an extraordinary set of conditions and timing? Or is it an inevitable consequence of chemistry, a natural law as fundamental as gravity? If it is the latter, then wherever the right ingredients and conditions exist, life should spontaneously arise. Perhaps in many forms we have yet to imagine. The transition from chemistry to biology also challenges our definitions of what it means to be alive. At what point does a collection of molecules cross the threshold from non-life to life? Is it when metabolism begins, when replication is possible, or when information can be stored and transmitted? These questions are not just academic, they affect how we search for life beyond Earth, and how we recognize it if we find it. Life elsewhere may not look like life on Earth. It may be simpler or more complex, organized in ways unfamiliar to us. Yet the underlying principle remains the same, a system capable of maintaining itself, reproducing and evolving over time. The spark of life then is not a singular event, but a dynamic process, a dance of molecules moving from chaos toward order, driven by energy and shaped by environment. This perspective opens the door to imagining life emerging in countless ways across the universe, each instance a unique performance of the cosmic symphony. But the story doesn't end with life's first breath. Once life begins, a new question arises. Can it evolve beyond its initial environment? Can these early life forms adapt, diversify, and transcend the conditions that birthed them? This question guides us into the next phase of exploration, where we investigate evolution, the mechanism by which life becomes ever more complex and diverse, transforming not just individuals, but entire ecosystems and worlds. Evolution is the master composer that takes the raw motifs of chemistry and biology and crafts the rich, complex tapestry of life as we know it, and perhaps as we have yet to discover. Life does not simply emerge and then remain fixed in place, like a frozen statue. Instead, it is in a constant state of flux, forever changing, adapting and refining itself in response to the environment. This continuous process of change is evolution, a powerful, elegant mechanism often described as nature's algorithm, tirelessly optimizing life to survive and thrive in an ever-shifting universe. To truly grasp the nature of life and its persistence, one must understand evolution not as a random walk, but as a purposeful process shaped by natural selection, mutation, and adaptation running over billions of years. Imagine evolution as an immense cosmic game of puzzles. The pieces in this case are traits, genes, and behaviors, each one a tiny fragment with potential to fit into a greater whole. But these pieces are not static. They constantly change shape through random mutations, genetic recombination, and environmental pressures. Some pieces fit better in the puzzle. Others fall away discarded by the unforgiving criteria of survival and reproduction. Natural selection acts like an invisible hand sifting through endless variations to choose the configurations best suited to the environment at that moment in time. Over countless generations, this trial and error process sculpts life forms, honing them into increasingly sophisticated and specialized beings. What is truly astonishing is that this algorithm requires no conscious designer. It is an emergent property of life's ability to replicate with variation, combined with the competitive pressures of limited resources. The rules are simple, yet profound. Organisms that better fit their environment tend to leave more offspring, gradually shifting the population's characteristics. Over time, this leads to the incredible diversity of life, from microscopic bacteria that thrive in boiling acidic springs to towering redwoods and complex mammals capable of self-awareness. If evolution is a universal principle, then the diversity of life across the cosmos could be virtually limitless, constrained only by the available ingredients and environmental conditions. Yet despite this staggering variety, some patterns and principles might remain consistent. For instance, life may universally require a way to store and transmit information, a mechanism for energy processing, and a capacity to reproduce. These shared features could be seen as the basic rules of the evolutionary game, ensuring life's persistence and adaptability, no matter where it arises. The implications stretch far beyond biology, touching on philosophy, and even the search for extraterrestrial life. If evolution is the cosmic algorithm, then wherever life exists, it is likely to evolve complex forms adapted to local conditions. This suggests that alien life might be as varied as the planets and moons themselves, each shaped by unique evolutionary histories, yet all connected by this common thread of change and adaptation. It also challenges us to reconsider our place in the universe, not as a pinnacle or endpoint, but as one node in an ongoing evolutionary story that spans space and time. But evolution's dance requires both time and stability. It is a slow, gradual process that unfolds over vast epochs, needing an environment that persists long enough for complex adaptations to emerge. This brings us to a crucial question. Does the universe itself provide the stability necessary for life and evolution to flourish? Or is cosmic chaos too great an obstacle, constantly resetting the stage before life can advance? This question sets the stage for our next exploration, where we examine the nature of cosmic stability and the conditions that allow life's delicate thread to weave its intricate patterns across time and space. Imagine the universe as an immense stage set for the grandest performance imaginable, the drama of life itself. But for this spectacle to unfold, the stage must be carefully arranged, the lights precisely tuned, and the scenery stable enough to support every scene and act. If the lighting flickers erratically, the sound distorts unexpectedly, or the scenery collapses mid-performance, the play falters and fails. In the cosmic theatre, this metaphorical stage is composed of fundamental physical constants and the stability of stars, planets, and galaxies that govern the environment where life might arise and evolve. Without this delicate balance, life would struggle to find footing, much less flourish. At the heart of cosmic stability are the fundamental constants numbers that dictate the strength of gravity, the electromagnetic force, and the behavior of atomic particles. These constants are not just abstract figures. They shape the very fabric of reality. For instance, the gravitational constant determines how matter clumps together to form stars and planets. If gravity were just a fraction stronger or weaker, stars might burn too quickly, or fail to ignite, while planets might be torn apart, or never form at all. Similarly, the fine structure constant controls how electrons interact with nuclei, affecting the chemistry essential for life. Alter these numbers slightly, and atoms might become unstable or fail to bond, erasing the chemical foundations upon which biology depends. Now picture this cosmic stage as a grand theatre where the laws of physics set the rules for the play. If the lighting system, the physical constants, is finely tuned just right, the actors, stars, planets, and ultimately life can perform their roles beautifully. But if the lighting is too harsh or dim, the show cannot proceed. This precision is astonishing, leading scientists to ponder why these constants seem so perfectly calibrated to allow the existence of life. This puzzle is known as the fine-tuning problem, a profound mystery at the crossroads of physics, cosmology, and philosophy. Beyond these constants, the stability of the celestial bodies themselves is critical. Stars must burn steadily for billions of years, providing a reliable source of energy to nurture life on orbiting planets. If stars were prone to violent, unpredictable outbursts or short-lived flashes, the fragile chemical and biological processes needed for life would be constantly disrupted. Similarly, planets need stable orbits to maintain consistent climates over vast timescales. Imagine living on a world where the seasons swing wildly between extremes, or the sun unpredictably fades and flares, making survival a constant gamble. The serene stability of our solar system is not just fortunate, it might be essential for the slow, patient work of evolution to unfold. This concept leads to a remarkable conclusion. If the universe's constants and cosmic structures are just right, neither too extreme nor too chaotic, then life might be not only possible but inevitable. In this view, life is the natural outcome of a cosmos that has the right settings. However, if the constants had different values, or if the celestial stage were more volatile, life as we know it might never have had the chance to emerge. This duality opens a fascinating debate. Is life a cosmic accident, a rare fluke in a chaotic universe, or is it the inevitable bloom in a garden carefully arranged by the laws of nature? This brings us to a deeper, more intriguing question. Why are these physical constants so finely tuned? Is it mere coincidence, or does it hint at something more profound about the nature of reality? Could there be countless universes, each with different rules, and we happen to inhabit the one where conditions are just right? Or is there an underlying principle, a cosmic design guiding these constants toward life-friendly values? This mystery invites us to peer beyond the boundaries of physics into realms of metaphysics and cosmology, setting the stage for the next chapter of our journey, exploring the possible reasons behind the universe's uncanny suitability for life, and what that might mean for our understanding of existence itself. Imagine tuning an old-fashioned radio one with a dial that must be adjusted with extraordinary precision to catch a clear station. Turn the knob just a fraction too far, and all you hear is static silence or a jumble of noise. Now envision the universe as this radio, broadcasting the signal of life across the vast cosmic airwaves. The physical constants and laws act as the dial settings, and astonishingly, they seem to be set at just the right frequencies to tune in life's signal with remarkable clarity. This phenomenon, known as the fine-tuning enigma, challenges our understanding of why the universe appears so exquisitely calibrated for life. The fine-tuning problem arises from the observation that the fundamental constants of nature, numbers governing the strength of forces like gravity and electromagnetism, the masses of elementary particles, and the rates of nuclear reactions fall within incredibly narrow ranges that allow the formation of complex atoms, stable stars, and ultimately life-supporting planets. Alter any of these constants slightly, and the delicate balance shatters. Stars might never ignite, or atomic bonds might never form, leaving a lifeless cosmos behind. This extreme sensitivity has led physicists, cosmologists, and philosophers alike to puzzle over whether such precision is a product of chance design or something more mysterious. One way to approach this enigma is to consider whether this fine-tuning is a mere coincidence, an extraordinary but random outcome in a vast cosmic lottery. Could it be that among countless possible values of these constants, we just happen to live in the one set that supports life? If the universe were like a dartboard, life's existence would be akin to hitting the tiny bullseye on the first throw. While improbable, some argue it is not impossible. Another perspective is that the universe's apparent tuning reflects an underlying intention or design, perhaps implying a purposeful creator or a deeper principle guiding the cosmos toward life-friendliness. This view, while speculative and controversial, taps into profound philosophical and theological questions about the origin and meaning of existence. Is the universe a conscious act of creation tailored to foster life and consciousness? Or is this perception simply a reflection of our limited perspective as life forms trying to make sense of their origins? Yet there is a third compelling hypothesis that seeks to reconcile the fine-tuning puzzle through the concept of the multiverse, a vast ensemble of universes, each with different physical laws and constants. In this cosmic landscape, often imagined in theories like eternal inflation and string theory, the universe we inhabit is just one station on the radio dial. Among countless universes with varying properties, only a small fraction would have the right conditions for life to emerge. Naturally, we find ourselves in one of those life-friendly universes simply because we could not exist in any other. This multiverse idea reshapes the way we think about fine-tuning and our place in the cosmos. Instead of viewing life as an improbable fluke or the product of design, it might be the inevitable outcome in a vast cosmic lottery with infinite tickets. It shifts the question from why is this universe so perfect for life to why do we observe this universe given the enormous variety of possible universes? Our existence acts as a selection effect known as the anthropic principle, meaning that the conditions we observe must be compatible with our presence as observers. The implications of this enigma ripple through science and philosophy alike. It forces us to confront the limits of scientific explanation, as the multiverse by its very nature may be beyond direct observation and testing. It invites us to consider that our universe might be just one chapter in a far grander cosmic story, a story with countless versions playing out simultaneously, each with its own physical rules and potential for life. As we stand at this crossroads, the fine-tuning enigma propels us to look deeper into the nature of reality itself. It opens the door to questions about the origin of the laws of physics, the possible existence of multiple universes, and the very definition of life in such a vast context. This mystery sets the stage for our next journey, exploring the bold ideas of the multiverse and how they transform our understanding of life existence and the cosmos beyond our observable horizon. Imagine walking through a sprawling cosmic marketplace, an endless bazaar filled with countless stalls, each one offering a unique and mysterious product. This bustling scene is a fitting metaphor for the multiverse, the astonishing idea that our universe is just one among an unfathomable multitude, each with its own set of physical laws, constants, and possibilities. In some of these cosmic stalls, life might flourish, while in others, the conditions are so alien or hostile that not even the simplest molecule could take root. This vision, both grand and humbling, opens a profound doorway into understanding why life exists at all, and whether it might be far more common and diverse than we have ever dared to imagine. The multiverse theory emerges as a bold solution to the fine-tuning puzzle, suggesting that rather than one universe finely balanced to support life, there exists a vast, possibly infinite ensemble of universes, each tuned differently. Some universes might have stronger gravity, others might lack atoms altogether, and yet others could have physical laws that defy everything we know. Within this endless cosmic marketplace, the odds of finding a universe that is just right for life increase dramatically, simply because of the sheer number of options. To grasp this concept more clearly, think of the multiverse as a lottery, but unlike any lottery you've encountered, this one has infinite tickets. The prize, a universe capable of nurturing life as we know it. The universe we call home might be one of the lucky winners, the fortunate stall in this infinite market, where the ingredients and conditions come together perfectly. If this is true, our existence becomes less of an extraordinary cosmic accident and more of a natural outcome of the vast number of universes trying out different recipes. The implications of the multiverse extend beyond mere scientific curiosity. If the multiverse is real, life might be far more common, not just on distant planets in our own universe, but in countless other universes as well. Each of these life-bearing universes could host forms of life radically different from anything we've imagined, shaped by the unique rules of their respective worlds. The diversity of life in the multiverse could be infinite, limited only by the variations in physical laws and initial conditions that define each universe. Yet while this grand vision is exhilarating, it also challenges our ability to comprehend and verify. The other universes in the multiverse, by definition, may lie beyond any observational reach, inaccessible to telescopes or probes. This means that the multiverse theory rests partly on the strength of mathematical models and indirect reasoning, rather than direct evidence pushing the boundaries of what science can empirically confirm. Nevertheless, it provides a powerful framework to understand why our universe seems so hospitable to life, because out of infinite tries, it's the one where life won the cosmic jackpot. Another intriguing question arises from this picture. Could life somehow traverse or influence other universes? Could the spark of life leap across the boundaries separating these cosmic stalls? Or is each universe isolated in its own bubble, a self-contained arena where life's drama unfolds independently? These questions push us deeper into the mysteries of cosmology and quantum physics, where ideas like quantum entanglement wormholes or cosmic inflation hint at subtle connections or bridges between universes, yet remain speculative and elusive. If life cannot cross these cosmic borders, it means each universe's biological story plays out in splendid isolation, a solitary thread woven into the vast cosmic tapestry. On the other hand, if there were mechanisms for life or information to spread between universes, it would radically reshape our understanding of life's resilience and its cosmic journey, opening the door to an inter-universal ecology or communication that transcends the confines of a single cosmos. As we stand at this frontier, the multiverse invites us to reimagine life, not as a rare accident confined to a solitary universe, but as a potential cosmic phenomenon, flourishing in myriad forms across an endless landscape of realities. This perspective humbles us by highlighting the vastness and variety of existence, yet it also inspires awe at the possibility that life's spark, once ignited, might be a universal theme echoing through the infinite corridors of the multiverse. This grand vision naturally leads us to the next crucial inquiry. Even if the multiverse offers infinite chances for life to arise, what does that mean for the possibility of life spreading or connecting across these universes? Can the boundaries that separate these cosmic realms be crossed, or is life destined to flourish only within the confines of its own universe? This question propels us into the fascinating domain of cosmic communication and potential inter-universal exchange, which we will explore next. Imagine the cosmos not as a collection of isolated islands floating in a vast void, but as a connected web where life's story unfolds as a journey across space and time. This idea that life might travel from one celestial body to another, hitching rides on asteroids, comets, or cosmic dust, is the heart of the panspermia hypothesis. It suggests that life's origins might not be confined to a single birthplace on Earth, but instead life's seeds could be scattered throughout the solar system, or even beyond, carried by the natural cosmic currents, like seeds blown by the wind from one tree to another in a sprawling forest. The concept of panspermia challenges the traditional notion that life emerged independently in one place, proposing instead that life, or at least its fundamental building blocks, could travel vast distances through space. This journey could take place aboard meteorites blasted off from planets by powerful impacts, or clinging to dust grains swept along by solar winds. In this cosmic ballet, life's ingredients, or even tiny microorganisms, might survive the harsh conditions of space travel, shielding themselves from radiation and extreme temperatures, only to land on a new world where conditions allow them to take root and flourish. To better visualize this, think about how dandelion seeds drift on the breeze carried by chance and wind currents until they find fertile soil to grow. In the same way, life might spread across the galaxy, carried by chance collisions and cosmic currents, creating a sort of interplanetary or even interstellar ecosystem, where life is not limited to a single origin, but a shared legacy traveling from world to world. The implications of panspermia are profound. If life is indeed a cosmic traveler, then the presence of life on Earth could be just one chapter in a much larger saga, suggesting that the solar system might be sprinkled with life's traces on worlds like Mars Europa or Enceladus, places where conditions could support life's growth once the seeds arrive. This transforms the search for extraterrestrial life from a lonely quest into a cosmic investigation into the movement and persistence of life itself. Furthermore, panspermia implies a remarkable resilience and tenacity in life's fundamental forms. It suggests that life can endure extreme environments and long periods of dormancy, waiting patiently for the right conditions to awaken. This resilience could mean that life's existence is more a matter of cosmic chance and distribution, rather than a rare, isolated miracle. The cosmic seeds could make life not a singular event, but a recurring theme woven throughout the galaxy. Yet panspermia also raises fascinating questions. How exactly does life survive the brutal journey through space? Could it be that life's building blocks originated somewhere else and came together here on Earth to spark biology? Or might life itself have traveled intact across the void? The answers remain elusive, but ongoing studies of meteorites containing organic compounds and experiments simulating space conditions suggest that life's building blocks are hardy and abundant. This leads us to ponder even further. If life can spread across planets within our solar system, could this process extend across the vast distances separating star systems or even galaxies? And if so, what forms might that life take? Could we encounter organisms radically different from Earth's familiar DNA-based life, adapted to environments utterly alien to us? This inquiry naturally brings us to the next great mystery, the possibility and nature of life forms, unlike anything we have ever seen, broadening our imagination about what life can be. As we contemplate the cosmic journey of life, it becomes clear that the story is not confined to the past or a single location, but a dynamic and ongoing voyage through the cosmos, inviting us to reconsider our place in the universe and the interconnectedness of all living things. The panspermia hypothesis, whether proven or not, expands the horizons of our search for life beyond Earth, urging us to look not just for life as we know it, but life as it might travel, transform and thrive throughout the cosmos. Imagine a world where life does not rely on the familiar building blocks we've come to associate with biology, here on Earth life that is not built from DNA or composed of cells as we know them, but instead exists in forms so alien and unexpected that they challenge our very definitions of what it means to be alive. This is the thrilling frontier of astrobiology and speculative science, a realm where life might be based on silicon instead of carbon, or exist in environments so extreme they would seem inhospitable or even hostile by terrestrial standards. What if the universal language of life isn't a single melody played on one kind of instrument, but rather a symphony with countless variations, each performed on entirely different instruments, each unique but still unmistakably alive in its own way? The notion of life as we don't know it invites us to reconsider everything we take for granted about biology. On Earth, life is carbon-based because carbon's chemical versatility allows for the formation of complex molecules like proteins and nucleic acids. But what if in the vast expanse of the universe, other elements serve as the backbone for life's chemistry? Silicon, for example, is often proposed as a candidate because it shares some chemical properties with carbon and can form long chains and complex molecules. Though silicon chemistry tends to be less flexible and more reactive at high temperatures in certain alien environments, it could potentially support forms of life utterly different from our own. To visualize this, Think of a song that can be performed on a piano, a guitar, or even a set of drums. The melody remains, but the instruments change the texture, tone, and feel of the music. Similarly, life song might manifest through different chemical instruments, carbon, silicon, or even exotic chemistries we haven't yet imagined. These alternative life forms could thrive in environments that would be lethal to us, such as the crushing pressure of a gas giant's atmosphere, the frozen methane lakes of Titan, or the superheated clouds of a volcanic exoplanet. The idea also extends beyond chemistry to the environments where life might exist. Life as we know it requires liquid water, moderate temperatures, and a certain range of atmospheric conditions. But what if life has found a way to flourish in liquid methane or ammonia, or even in the plasma storms of stars? These extreme habitats could harbor organisms with radically different metabolic processes, energy sources, and survival strategies. Perhaps life that feeds on radiation or uses magnetic fields to sustain itself. Such possibilities stretch the imagination and force us to rethink the universality of life's recipe. The implications of recognizing life beyond our earthly template are profound. If life can take on such varied and alien forms, then the cosmos could be teeming with biological diversity far beyond what we've ever dreamed. This would mean our current search methods, which often look for Earth-like biosignatures, such as oxygen or methane in exoplanet atmospheres, might miss entire kingdoms of life existing under different rules. It pushes scientists to develop new tools, new theories, and new ways of detecting life that don't depend solely on carbon chemistry or Earth-like conditions. This expanded view also challenges philosophical and existential perspectives. If life can exist in many different forms and places, what does it mean for humanity's uniqueness? Are we the rule or the exception? Could there be ecosystems thriving in places we've never thought to look? Ecosystems that evolved independently, and perhaps more than once, each singing its own cosmic song. The discovery of life so different from us would not just be a scientific revolution, but a profound cultural and philosophical shift, reshaping how we see ourselves in the vast cosmic arena. Yet this broad horizon of possibilities brings with it a major question. How do we recognize and confirm such unfamiliar life? Our current instruments and missions are primarily designed with Earth-like life in mind. What kinds of signs or markers could indicate life that does not breathe oxygen, does not metabolize carbon, or does not rely on water? Could we detect unusual chemical imbalances in planetary atmospheres, unexpected energy emissions, or bizarre surface features that hint at biological processes foreign to us? As we prepare to venture deeper into space with advanced telescopes, robotic explorers, and potentially human missions, the search for life, as we don't know it, demands open minds and new strategies. It encourages interdisciplinary collaboration among chemists, biologists, astronomers, and even computer scientists who model life's potential forms. It invites us to develop biosignature frameworks that are flexible and inclusive, capable of capturing life's diverse manifestations. This challenge leads naturally to our next question. Once we imagine life in forms utterly different from our own, how do we design the tools and methods to seek out and identify these mysterious life forms? What instruments will pick up the whispers of alien biochemistries, and how will we interpret those signals without Earth-centric bias? The journey to answer these questions will shape the future of astrobiology and deepen our understanding of life's true cosmic potential. When we look up at the night sky, the vastness of the cosmos stretches out before us like an endless ocean of mystery filled with countless stars and planets. It's natural to wonder, are we alone? For decades, humanity has been engaged in a profound quest to detect signs of life beyond Earth, a pursuit that often feels like trying to hear the faintest whisper in an enormous bustling forest. The challenge of detecting the undetectable, finding life on distant worlds, pushes us to innovate and rethink how we listen, look, and interpret signals from the universe. The search for extraterrestrial life is not merely a matter of peering through telescopes or sending robotic probes. It is a complex endeavor that blends cutting-edge technology, clever science, and an ever-evolving understanding of what life itself might be. Our traditional efforts have included projects like the Search for Extraterrestrial Intelligence, or SETI, which scans the skies for narrow-band radio signals or laser pulses that might indicate the presence of technologically advanced civilizations. The underlying idea is simple yet profound. If other civilizations are out there, perhaps they are broadcasting messages or unintentionally emitting signals that we can detect. SETI listens intently, tuning into the cosmic radio waves in hopes of catching a sign that we're not alone. But this approach faces a huge challenge. The cosmic noise is vast, and the signals we might seek could be extremely faint, intermittent, or encoded in ways we don't yet understand. Besides listening for artificial signals, scientists also look for chemical fingerprints in the atmospheres of exoplanets, planets orbiting stars beyond our solar system that might reveal biological activity. When we observe distant worlds, we try to identify gases like oxygen, methane, or other molecules that on Earth are closely tied to life. The hope is that by detecting these biosignatures, we can infer the presence of life, even if we cannot see it directly. Yet this method too is fraught with difficulties. Non-biological processes can sometimes mimic these signatures, and the atmospheres of distant planets are often shrouded in layers of clouds or hazes that obscure our view. It's like trying to hear the song of a single bird from miles away, when 1,000 other creatures are singing their own melodies nearby. We also send robotic explorers to nearby worlds such as Mars, probing the soil and atmosphere for organic molecules, searching for evidence of past or present life. Instruments like spectrometers, microscopes, and chemical analyzers on these rovers are designed to sniff out the subtle clues that life might have left behind. Yet even on Mars, the search has yielded tantalizing hints, but no definitive proof. It reminds us that life, especially beyond Earth, might not be shouting its presence, but quietly whispering, requiring patience, precision, and sometimes new ways of looking. The analogy of listening for a bird's call in a vast forest captures the essence of our predicament. The universe is teeming with electromagnetic noise, cosmic background radiation, and signals from countless astrophysical processes. We have to differentiate between natural cosmic sounds and the possible voices of life. This requires not only sensitive instruments, but also clever algorithms and artificial intelligence that can sift through mountains of data to spot patterns that stand out from the cosmic chatter. An additional complication is that our search is inevitably biased by our own experience. We look for life that behaves or appears in ways familiar to us, based on carbon chemistry, water as a solvent, and technological emissions that mirror our own. But as we've seen, life might be stranger and more diverse than we imagine. If so, then we may be scanning the skies with blinders on missing subtle signs that fall outside our current understanding or technical capabilities. This realization brings an important, humbling truth. We might be looking in the wrong places or using tools that are insufficient. The universe could be rich with life yet remains silent to our ears because its signals are in languages we have not yet learned, or its presence is masked by phenomena we cannot easily distinguish. This invites innovation in both technology and thinking new telescopes capable of higher resolution and broader spectral coverage, new probes designed to explore extreme environments, and new theoretical frameworks that expand what we define as life and intelligence. Even as we develop more advanced instruments, the vast distances and immense timescales involved impose fundamental limits. A signal emitted thousands or millions of years ago might never reach us, or the civilization might no longer exist when we receive it. Likewise, life might exist in forms or scales that are difficult to detect remotely, or it might communicate in ways completely alien to us, such as through quantum phenomena or biochemical signals beyond our current instruments. This brings us to one of the most profound and enduring questions of all. If life is common in the universe, and if intelligence and technology arise elsewhere, then why haven't we encountered clear evidence yet? The silence we observe is sometimes called the Fermi Paradox, a puzzle that challenges us to reconcile the vastness and age of the universe with the apparent absence of detectable extraterrestrial life. It might be that intelligent life is rare or transient, or that civilizations are deliberately avoiding contact, or simply that our methods and time frame for detection are too limited. In facing this paradox, our quest to detect the undetectable is as much about expanding human imagination and perseverance as it is about scientific instruments. It teaches us to question assumptions, to embrace uncertainty, and to keep exploring with open minds. Whether or not we find life soon, the journey enriches our understanding of ourselves, our planet, and our place in the cosmos. As we look forward, the question evolves: how do we refine our search strategies to broaden our reach? How do we invent new ways to sense life that may be whispering to us in forms or languages we have yet to comprehend? The challenge of detecting the undetectable pushes us not just to build better telescopes and landers, but to rethink what it truly means to listen, to see, and to recognize life beyond the familiar confines of Earth. The night sky, vast and glittering with countless stars, presents a paradox that has puzzled scientists and philosophers alike for decades. If life is indeed a common outcome of the universe's laws and chemistry, why does the cosmos seem eerily silent? This profound question is captured in what we call the Fermi Paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights a glaring contradiction given the age of the universe and the vast number of potentially habitable planets. Intelligent life should have emerged countless times and presumably made its presence known. Yet our searches yield no definitive evidence, no signals, no signs of visitation. Imagine a sprawling city teeming with streets, buildings, and homes, but not a single voice echoes through its alleys. The silence is deafening and deeply unsettling. At its core, the Fermi Paradox forces us to confront the uncomfortable possibility that intelligent civilizations, if they exist, might be extraordinarily rare, short-lived, or perhaps simply choose to remain hidden. This paradox opens the door to a wide range of hypotheses, each trying to explain the cosmic silence. Some suggest that technological civilizations inevitably self-destruct before they can spread across the stars, caught in cycles of war, environmental collapse, or catastrophic accidents. Others propose that advanced civilizations deliberately avoid contact, adhering to some cosmic form of quarantine or zoo hypothesis, where Earth and humanity are observed but not disturbed. There are also ideas that the universe might be teeming with life, but most of it exists in forms or realms we cannot perceive, perhaps as digital consciousness, or in dimensions beyond our grasp. The paradox also challenges our assumptions about intelligence and communication. Maybe the pathways to technological advancement are not inevitable. Perhaps intelligence capable of interstellar communication or travel is an exceptionally rare evolutionary accident, or it may take form so alien that we fail to recognize its signals. Our own history, after all, is but a brief flicker on the cosmic timeline, and the window during which a civilization emits detectable signals might be minuscule compared to the age of the universe. We might be simply too early or too late to hear the cosmic chorus. The image of a bustling city with no voices forces us to reconsider the nature of life's progression and the future trajectory of humanity. If intelligent life is rare or fleeting, what does that say about our responsibility to preserve and nurture our own civilization? The silence around us may be a sobering reminder of how precious and fragile life is, a call to stewardship for our planet and our future. On the other hand, if advanced civilizations exist but remain silent or hidden, it raises questions about their motives, their understanding of existence, and what role we might play in a broader cosmic community. The implications stretch far beyond science and technology into the realm of philosophy and existential reflection. The Fermi Paradox pushes us to ask not just if we are alone, but what it means to be alive and intelligent in a vast, indifferent universe. It compels us to explore whether our search for extraterrestrial life is ultimately a search for ourselves, a quest to understand our place in the cosmic story. The silence of the stars may also inspire hope and determination. It challenges us to become the explorers and communicators that others might have been, to reach out boldly and responsibly to ensure that the story of intelligent life continues and expands. As we ponder the paradox, it becomes clear that while life itself might be a natural and widespread phenomenon, intelligence, especially of the kind that can build civilizations, create technology, and communicate across the stars, may not be. The emergence of consciousness capable of pondering its own existence might be the rare spark in the vast dark, a unique beacon flickering in the cosmic night. This realization shapes our approach to the future, urging us to cherish our uniqueness, to safeguard the fragile flame of intelligence, and to embrace the profound mystery that lies ahead. This leads naturally to the next profound question. If life itself is common, but intelligence is rare, what does that mean for our search for our understanding of evolution and for the destiny of life in the universe? It is a question that drives us onward, pushing the boundaries of science, philosophy, and hope as we continue to listen for that elusive, distant voice in the silent city of stars. The question of whether intelligence is a rare jewel in the cosmic landscape or a common milestone in the evolution of life is one of the most profound puzzles confronting science and philosophy. It challenges us to reconsider our assumptions about the natural progression of life and the significance of human consciousness within the vast expanse of the universe. Is intelligence, with its capacity for abstract thought, complex communication, and technology, the inevitable summit of evolutionary processes? Or is it merely one of many evolutionary paths, a delicate and unlikely outcome amid countless others? To explore this, we can imagine the journey of life as a river's flow. This river might eventually find its way to the vast open ocean, representing the rise of intelligent beings and civilizations. Yet it could just as easily dissipate into the sands of a desert, never reaching that distant horizon. Life on Earth offers a compelling case study. For billions of years, life existed in simple forms: microbes, algae, and early multicellular organisms. Intelligence in the form of advanced cognition and technological innovation appeared relatively recently, and only in one lineage, humans. This suggests that while life might be abundant, the emergence of intelligence capable of reshaping the environment and contemplating its own existence might require an extraordinary confluence of factors. The evolution of intelligence could depend on a complex interplay of environmental pressures, genetic mutations, social structures, and sheer chance. Unlike the broad and robust spread of life's simpler forms, intelligence may be an evolutionary dead end for many species, or simply a path less traveled. The implications of intelligence being rare are profound. It would mean that while the universe might be teeming with life in various shapes and sizes, the companionship of truly intelligent life could be exceedingly scarce, leaving us as cosmic islands amid a sea of microbial or non-sentient beings. This scenario paints a picture of profound loneliness, where the vast silence we observe is not due to a lack of life, but the absence of minds like ours, capable of communicating across the stars. It challenges the popular notion that the cosmos should be bustling with chatter signals and contact from countless civilizations. Instead, it suggests that the spark of intelligence is fragile, rare, and perhaps fleeting. On the other hand, if intelligence is a common outcome, then the universe could be alive with a multitude of minds, each following its own evolutionary journey. These civilizations might be diverse in form and culture, with technologies and social systems unimaginable to us. The shared thread would be a kind of cognitive spark that elevates beings beyond mere survival, enabling them to explore, innovate, and perhaps communicate across the cosmic void. In this scenario, intelligence could be seen as a natural evolutionary attractor, a convergent phenomenon much like the evolution of wings in birds and bats. Distinct origins leading to similar solutions driven by the demands of survival and adaptation. Whether intelligence is rare or common, this question touches deeply on what it means to be human and what role we might play in the cosmos. If intelligence is rare, our existence becomes all the more precious and urgent, a singular opportunity to preserve and nurture a fragile consciousness capable of wonder and understanding. The responsibility to safeguard our planet to advance ethically and technologically takes on a cosmic significance. If intelligence is common, then our journey is part of a much larger story. One of many civilizations striving, thriving, and perhaps reaching out to one another across the darkness. This leads us inevitably to the next crucial question. If intelligence exists elsewhere, can it communicate with us? Are there ways that other intelligent beings might influence, inspire, or even shape our own development? The possibility of interstellar communication, or at least the detection of signals from distant civilizations, has long fueled both scientific inquiry and the human imagination. Could we be part of a cosmic conversation? Or are we isolated in our own corner of the universe, waiting for a response that may never come? Understanding the nature, rarity, and potential reach of intelligence shapes how we search for life beyond Earth, how we interpret silence, and how we envision humanity's place in the grand cosmic narrative. The idea that the universe might be teeming with life, yet the vast cosmic silence persists, leads us to a perplexing and deeply intriguing question. Are we truly listening? And if so, are we even capable of understanding the language of the cosmos? The search for extraterrestrial intelligence, often abbreviated as SETI, has been a monumental human effort to tune in to signals beyond our world, scanning the skies for anything that might resemble a message from an intelligent civilization. Yet despite decades of listening, the stars remain silent, or so it seems. This silence may not be an absence of communication, but rather a profound problem of language interpretation and the sheer scale of the universe itself. Imagine two strangers on opposite sides of a vast canyon trying to communicate through signals without words. They might wave hands, flash lights, or tap rhythms, but without a shared language or understanding of context, their messages could be confusing, misunderstood, or completely missed. This metaphor mirrors the challenge humanity faces in trying to decipher potential cosmic signals. Even if advanced civilizations are transmitting, we may lack the common framework to recognize or interpret their signals as communication. What if their language is encoded in frequencies or patterns so alien to us that our instruments can't detect them? Or perhaps their messages are transmitted in ways that do not align with our concepts of communication, through quantum states, neutrinos, or something else entirely beyond our current technology. The problem is compounded by the immense distances involved. Light travels fast, but the universe is vast. A message sent from a civilization 100 light years away takes a century to reach us. By the time we receive it, the civilization that sent it may have changed, moved on, or no longer exist. Communication in this sense is not just about language, but about timing, synchronization, and the patience to listen across the epochs. Even if we were able to send a reply, it might take centuries, if not millennia, for our response to reach its destination. This delay challenges our expectations of dialogue as a back-and-forth exchange and forces us to think about communication on timescales far beyond human lifespans. Another dimension to this challenge is the assumption that extraterrestrial intelligences would use electromagnetic signals, like radio waves, to communicate. This assumption stems largely from our own technological history, but it may be a blinkered perspective. Other civilizations might use forms of communication we cannot yet conceive, perhaps manipulating gravitational waves, harnessing dark matter, or employing technologies so advanced they appear as natural phenomena to us. The diversity of possible communication methods expands the complexity of detection exponentially. Our current searches, as sophisticated as they are, cover only a fraction of the possible languages the universe might be using. If we consider the possibility that we are surrounded by life forms, perhaps even intelligent ones, but remain unable to understand them, the notion of cosmic solitude shifts. We may not be alone, but the barriers to interaction, linguistic, technological, temporal, are so immense that it feels as if we are isolated in a silent void. This language barrier creates a kind of cosmic solitude, not due to the absence of others, but because of the insurmountable challenges in bridging the gaps that separate us. This leads to profound implications for how we search for life and what we expect to find. Instead of simply listening for signals, we can recognize perhaps we need to rethink our approach, developing new theories and technologies that expand our understanding of communication itself. Could artificial intelligence help detect patterns too complex or subtle for human analysts? Might we look for indirect signs of intelligence, megascale, engineering, unexplained astrophysical phenomena or anomalies in energy usage that suggest a presence beyond conventional signals? The quest for cosmic communication might not only reveal others, but also expand our own understanding of intelligence and language in unprecedented ways. Beyond the technical and scientific challenges, the silence, or perhaps the misunderstood noise, invites reflection on the human condition itself. Our desire to connect with others across the stars speaks to a fundamental yearning for meaning and companionship in the vastness of space. The possibility that we are listening yet unable to understand encourages humility. It reminds us that intelligence and communication might be far more diverse and complex than our narrow earthly experience suggests. This silent dialogue, the cosmic conversation that might be unfolding beyond our grasp, frames a broader contemplation. What is the meaning of life in the universe? If the cosmos is full of life yet communication remains elusive, does this change how we view our existence? Are we isolated observers, fortunate to have consciousness, or participants in a grand cosmic symphony that we have only just begun to hear? The silence compels us to think deeply about the nature of life, intelligence, and connection, urging us toward greater curiosity, innovation, and patience as we continue our search. Ultimately, this inquiry prepares us for the final reflection, the quest not just to understand if we are alone, but to understand why we are here at all. What role does life, intelligence, and communication play in the grand unfolding of the cosmos? The silent dialogue echoes a timeless question that transcends science in a universe so vast and mysterious. What is the meaning of our brief shining existence? When we step back to gaze at the cosmos as a whole, we confront an immense tapestry woven with countless stars, swirling galaxies, and vast stretches of seemingly empty space. Amid this staggering scale, our own existence can seem fleeting and insignificant, like a tiny flicker in an unfathomably vast night sky. Yet if life is indeed an inevitable outcome of the universe's grand design, an intrinsic feature of the cosmic landscape, rather than a mere cosmic accident, then we begin to realize that our smallness is not a mark of insignificance, but rather a subtle, profound place within a much larger story. Like a modest star in a sprawling galaxy, we may be small in size, but we are no less brilliant, no less meaningful. Our light, our consciousness, and our curiosity ripple outwards, illuminating the darkness in ways that reverberate far beyond our individual selves. This reflection on our place in the cosmos invites us to see ourselves not as isolated anomalies, but as natural expressions of the universe's capacity for life. It challenges the traditional human narrative that often places us at the center of all things, instead suggesting a humbler yet more wondrous perspective. We are threads in an enormous cosmic fabric intimately connected to the stars and planets, formed from the very elements born in ancient stellar furnaces. Our bodies, our minds, even our dreams are extensions of cosmic processes stretching back billions of years. This connection imbues our existence with a sense of continuity and belonging, grounding the question of who are we in a grander universal context? Philosophically, this idea reshapes how we view the meaning of life. If life is not a rare anomaly but a cosmic imperative, then perhaps meaning itself is embedded in the very act of living, evolving, and seeking understanding. The universe may be viewed not merely as a cold, indifferent expanse, but as a dynamic arena where life unfolds as a fundamental and beautiful expression of cosmic possibility. Each organism, from the simplest microbe to the most complex human brain, becomes part of a universal narrative that is continuously written and rewritten. Our ability to ponder existence, to question and dream, is not an accident, but an essential chapter in this unfolding story. In this light, the quest for meaning is simultaneously intimate and universal. On a personal level, our lives gain depth through the connections we forge, the knowledge we pursue, and the legacy we leave behind. Yet on a cosmic scale, our existence resonates as a beacon of life's persistence, adaptability, and mystery. We embody the universe's remarkable capacity to know itself, a self-awareness that might be rare but is undeniably profound. This duality, our intimate humanity entwined with cosmic vastness, offers a unique kind of meaning that transcends simple answers. It suggests that the search itself, the willingness to explore, question, and embrace the unknown, is the heart of life's purpose. The implications of this perspective stretch beyond philosophy into how we approach our future and our responsibilities. Recognizing that life is a precious and perhaps inevitable outcome of cosmic evolution can inspire a deep respect for all forms of life and the environments that sustain it. It encourages stewardship of our planet and the broader universe, fostering a sense of kinship not only with other humans, but with all living beings and the very cosmos that nurtures them. This awareness could unify humanity in a shared mission to explore, preserve, and celebrate the wonder of existence, transforming how we relate to each other and to the universe. Moreover, the idea that life might be an ongoing cosmic phenomenon invites us to imagine the future in bold and hopeful terms. If life is woven into the fabric of the universe, then our story is part of an endless chain stretching forward into unknown realms and possibilities. Perhaps one day our descendants will spread life across the stars, extending the spark of consciousness and creativity into the far reaches of space. This vision casts humanity as participants in a magnificent and eternal drama, where every act of curiosity, compassion, and creation contributes to the unfolding mystery of existence. Yet even as we contemplate such grand prospects, the question remains open-ended and ever enigmatic. The meaning of life, much like the universe itself, is a mystery that deepens with every discovery. Each answer leads to new questions, each revelation to new frontiers. Life might be the universe's greatest question and its most beautiful response, a paradox that invites us to live fully and thoughtfully, embracing both the certainty of our smallness and the wonder of our significance. In this cosmic reflection, we find a narrative that honors the grandeur of the stars and the fragile spark of life. We are reminded that our story is part of something far greater than ourselves, a story of transformation, resilience, and awe. As small as a single star might seem within the vast galaxy, its light travels across the darkness, touching distant worlds and illuminating the infinite. In much the same way, each of us, though tiny, against the backdrop of the cosmos, shines with a light of our own, contributing to the boundless symphony of existence. Ultimately, the meaning of life may be less about finding definitive answers and more about participating in this grand cosmic journey. We are not just observers, but actors, co-creators, in a universe that continually unfolds in mystery and wonder. Each breath we take, each thought we have, and each connection we make adds a note to the universal melody that has played for billions of years and will continue long after we are gone. So as we stand beneath the endless sky, gazing at the stars, we can find solace and inspiration in knowing that we are part of a magnificent story, one of life, of eternity, and of the unfathomable beauty of the cosmos. Every one of us, no matter how small or fleeting, carries within us the echo of the universe itself, a radiant spark in the vast cosmic night. This is the inevitable meaning of life, to shine, to wonder, and to be a living testament to the magic of existence.